Morning, everybody. We are beginning our final section of the year, 6.3. We're going to have 3 days of videos again, followed by a worksheet day and a quiz day. This Friday is considered a reading day, so you will not see a posting from me. Just continue to catch up on any work that you have, but there will not be a video or a worksheet or anything for me to complete for this Friday. So you'll see a video today, Monday, and a video on Wednesday this week. Okay. So our final section is about volumes of revolution. So again, we're going to be integrating an area to create a volume. The last section, the area changed because the shapes, the cross sections could be triangles, semicircles, squares, rectangles, you name it, it didn't matter. And if we integrated that shape, then we would get the volume of the solid. But now, since we have a revolution, something rotating, every time we have a slice in these problems, our slice will be a circle. So these problems get easier in the sense that all of the areas that are going inside of our integral will always be about circles. So you have to figure out what the radius is and what the limits of integration are. So I'm going to have you guys visualize two different types of problems depending on the direction that we are rotating. So if we are rotating vertically, which would mean it's rotating about a horizontal axis, I want you to envision yourself jump roping, where your hands are the x-axis, they're kind of remaining still, and that jump rope is swinging around your body. And the jump rope's shape by itself, two-dimensionally, would be a parabola. And the vertex of that parabola is going below your toes, above your head, below your toes, above your head. And the shape that it's creating as it's rotating is a large circle, right? And as we move left or right around that parabola from the vertex, the circles get smaller, but they're still circles. And the circles near your hands, near those limits of integration, are the smallest, and they're approaching zero. So that's one type of rotation that I want you to envision, is a jump rope. That's a vertical rotation. The other one that I want you to envision would be a carousel. So any old-fashioned carousel that you see at Six Flags or at the mall, you're sitting on that horse or that rooster, whatever animal you pick, but that one is rotating horizontally around a vertical axis. So the pole in the middle would be like the y-axis. And if you're somebody sitting on the outer edge, your circle is the largest. If you're somebody sitting on the inside, next to the pole, your axis, or your circle, your rotation is a little bit smaller. But nonetheless, we have circles in there. Those are horizontals. So the first example that I gave you, if we are a jump rope rotating vertically, our radius is running up and down. So therefore our radius is a y equals radius. If we are on the carousel, our radius is running left to right. So we are an x equals radius. So that's a ton of information without me writing anything down, but hopefully that will give you a visual of what we are about to do. And here's your formula. So there's going to be two different types of problems in this section. A disk, which is solid, like the jump rope. So when we are finding our area, we are finding the area of a circle that doesn't have a hole. Okay, the other type, I'll tell you now so you have an idea of what I'm alluding to, is a washer or a donut. So that would look like this. And we would be looking to find this area. So that's for another day. Or not even another day, I'm sorry. I think later in this lesson I'm going to do a disk and a washer problem here in the same direction. So for now, the formula, like I said, is we are integrating the area formula. And the area formula is always a circle. So in this case, pi r squared. We're going to use capital R because it's the largest circle that you'll see if we're talking about disk versus washer. Okay. The pi could be inside of the integral or outside. That's up to you. It doesn't really matter. The second equivalent way of saying this is pi from integral from a to b f of x squared. Because the radius will be dependent upon what the function is. The radius will not be just a number, it'll be what the function is. Okay. Another way to think about it, the radius will always be distance from axis of rotation to the function. Okay. So here's your steps. You're going to sketch it. So when I say sketch it, I always mean that two-dimensional graph. So if the problem is giving you a parabola, a line, whatever the case is, go to Desmos, do it by hand, or your graphing calculator, and get a sketch of that. Okay. Then we're going to sketch the solid that we would be forming by rotating the region. Mostly here, we're going to reflect first, two-dimensionally reflect about the axis of rotation, and rotate. When that rotation is happening, again, there's circles. So we're going to take one circle slice, or circular slice. Find the formula for the area of the cross-section. Again, it's pi r squared. But what is r? That's the big question. Once we have that, we're integrating. Okay. So here's our first example. There are steps still here. Calculate the volume of the solid obtained by rotating the region under y equals x squared about the x-axis from 0 to 2. So some keywords here. The region under, the graph, of course, the function is very important. The axis of rotation, and our limits of integration. All of those are relevant. Start with y equals x squared. Then block off your limits of integration, right? 0 until 2. I don't know exactly where it is, but right there. Okay. Highlight the area underneath, the region that they're referring to. Right, so that's the two-dimensional solid that is going to be rotating, and it's rotating it about the x-axis. So the first thing you could picture happening would just be a simple reflection. If I reflected that graph over the x-axis, I would have that green region, sort of like a mirror image right below. So all I'm doing is reflecting the part of the parabola that I care about below the x-axis, and then I am finished shading in. So now I have a two-dimensional space that has been reflected. And if you can imagine this portion of the parabola spinning, you would be getting circles. It would look like a funnel, a sideways funnel. Okay? So, in this picture is where they wanted me to blow this picture up a little bit. So this is essentially what we have. Okay? So when we say cut and turn, again, they're always circles, okay? The direction that you draw the radius is important to me. So basically where the center of the circle is our axis of rotation. Our radius is running vertically because that's how our graph is rotating. 1 second, guys. Okay, you're welcome. So the direction of my radius is dependent upon the direction of the rotation. So it's a vertical rotation about a horizontal axis, which makes my radius vertical. The only reason that really helps me is that helps me decide that my radius is then a y equals equation, which is typically how these equations are given, y equals x squared. In this section, you will not have to double your radius ever. It's already cut in half by nature of rotation. If you're rotating it about something, it's going to give you that mirror image above and below. In essence, bisecting your circle, which naturally gives you a radius instead of the diameter. There will be vertical or horizontal translations, shifts, so a radius can get larger by a number or smaller by a number, but you will not be multiplying or dividing by 2. Okay. So here we have our slice, we have our radius. Formula is always the same, pi r squared. In this case, r is x squared. So you could simplify this to pi x to the 4th. And that goes into your integral. Again, you could put pi in there, or keep pi out. Just don't forget about pi. Most common mistake here is we forget about pi. Okay. I always keep this step for last. I put my area formula in. I look at the variable that is inside of my integral. So that means I have x's right now. And I go to my x-axis. I'm looking for x numbers. Because it's not always the clear-cut interval that's given. You know, if that's given, it's there. But if they don't give it to you, you have to be able to find it. So I'm going to my x-axis. I'm going the far left number and the far right number, the extremes of this graph. Where does it begin? Where does it end? So it begins at 0 and it ends at 2. So you get an answer of 20.1. And that's with pi. This is a visual of a washer problem. So in this portion, we have, let me color code, we have 2 different functions. So I don't have all the functions here, I just have the picture. I have function red, and I have function blue. My red, which is the outer, is the f of x. And my blue, which is the inner, is the g of x. Right, so my red, which is higher up, as it rotates about the x-axis this example has, the red ends up rotating at a farther distance, so it makes the larger radius. The blue rotates closer together because it's closer to the x-axis. Like I wrote down as the definition before, distance from axis of rotation to the curve, to the function. So right here at point x, the distance from point x, in a vertical sense, the x is at 0 in terms of y, up to point b would be whatever the function f of x is, right? The y coordinate of it, it's a height. Likewise, for blue, it would be whatever the point A is, but it's a smaller thing. So we would figure out that radius with respect to f and with respect to g. Okay. Big R squared minus little r squared, because all we're doing here, this is like a bullseye problem. Right? This was a typical geometry problem when you were learning about area of circles. We only want the area of the shaded region. We don't want the area of the inside circle, so we don't want the area of the blue circle. We want red, so we would want pi big R squared, and we would take away pi little r squared is the way that I will refer to these. Big R squared, little r squared. Right, and so the formula up top there is just condensing this and saying, well, I don't need to put pi next to both of them. I'm factoring that pi out, and then I have big R squared minus little r squared will give me the area of the green shaded region, just like they have in the example. Okay. So these are called washer problems, or donut, or whatever you want to think about. There's a hole in the middle. So let's take a look at this. We have x squared plus 4 and y equals 2 from 1 to 3. And we're still rotating it about the x-axis. So go to your graphing calculator if you need to, or get a rough sketch. X squared plus 4 is our parabola shifted up 4 units on the y-axis. The 4 is very significant, mostly because we now have a horizontal line at 2. So we needed to know that this would be below. That's very important. And the region is only from 1 until 3. So those are like vertical asymptotes. They bound the space that we are focusing on, 1 and 3. So the region between x squared plus 4 and 2 from 1 to 3 would be right here. Right? It's key that you figure that space out. Okay. Once we have that space figured out, we reflect about that axis of rotation, which in this case is the x-axis. So we create symmetry below the x-axis. So the first thing which in my mind here is the easiest to reflect would be that horizontal line of 2. And I'm only going to draw it in the space I need to. So the original y equals 2 is 2 units above the x-axis. My new reflected line is 2 units below the x-axis. I don't have to number all that. It's not that important, but I want to make my picture pretty accurate. Okay, then I have the piece of the parabola right there. Again, it doesn't have to be perfect, but I have a relatively symmetrical sketch. Okay. And then the last thing that I would definitely sketch would be as visualize this rotating, right? Blue to blue. Even if you only put one circle in there. Blue to blue rotates, red to red rotates. Notice the empty space that I did not shade. We only want to find the volume of the green. So if I slice this, right, and I draw my circles flat on my page, most importantly, I draw my radius in the direction of the rotation or the direction of the slice. What way do I have to slice this in order to get a circle? If I sliced horizontally, I wouldn't have a circle. If I sliced vertically, I would have that circle because of the rotation. Okay, so I have to figure out, well, what is big R and what is little r? Again, my slice is vertical, so I get to use y equals for these. Typically, our equations are given with y equals, and you don't even have to change it. So big R, blue, is the parabola. So it's y equals x squared plus 4. Little r, red, is the line. It's y equals 2. So my inside circle is always the same size because it is made from a horizontal line, a numerical value. My outside circle, as I move towards the number 3, my right limit of integration, I have my largest circles. As I move left towards 1, I have my smaller circles. Not drastically in this case, but smaller. So anyways, taking this idea here that we have big R and we have little r, and we are looking to find the area of the shaded green. So I would have pi quantity x squared plus 4 squared minus 2 squared. Big R, little r, both of them squared by themselves. I take that formula and I put it in my integral. You can simplify 2 squared to 4. I have x's in my integral, so it is a dx. Okay, the other thing, I have x's in my integral, so I need x limits of integration, 1 and 3. Careful simplifying these. So many of you all are tempted to say that this is x to the 4th plus 16. Right? It's not. It's not. So just leave it as a quantity. In order to simplify this correctly, you would have to expand it and FOIL it out. In this section, just leave it. Don't try to simplify unless it's as easy as 2 squared is 4. $445.27. Okay, good. Okay, one more example. This one, it's still a vertical rotation. We still have a horizontal axis, but our horizontal axis is now -3. So our axis of rotation changed. Okay. So all 3 pictures are here. Sometimes that's helpful, sometimes it's a little bit more intimidating, but let's walk through them. So the problem says, find the volume V of, they call this the wedding band, obtained by rotating the region between the graphs of f of x equals x squared plus 2. So let's do f in red. So x squared plus 2. And g of x in blue is 4 minus x squared. Okay. In this case, we don't have domain restriction or limits of integration because these intersect. If it wasn't clear that they already intersected at -1 and 1, we would have to set them equal to each other and solve for those intersecting points, or go to the graphing calculator and find them. Okay, but here, the graph shows us it's -1 and 1. Okay. And now the other key is that we are not rotating it about x-axis, we're rotating it about -3. So again, I'm going to go back to that definition of the radius, the distance from the axis of rotation to the curve. So as one example, right, the radius changes no matter, or depending on where you are on the parabola. I'm just drawing the radius at the vertex right now. So 4 minus x squared in blue. That distance would typically be from x-axis up. So when I'm on the y-axis, that means my x value is 0. That means this distance is 4 initially. But now if I move down to -3, did my radius get bigger or smaller? Did it get longer or shorter? So in this case, my distance expanded by 3 units. And that would be the case anywhere, right? All of the radii that I could draw here, all the way down to -3, would be larger this concept directly relates to 6.1 when we did top function minus bottom function. Curve minus axis of rotation in this case. 4 minus x squared minus a negative 3 becomes plus 3. Okay? So you can think of it that way, or you can think of it the way I just explained it visually. Even though the axis of rotation is negative, my radius is larger because it moved further away. Okay, so we'll come back to that in a second. What we have to do now, I'm going to erase the, maybe I'm not. Okay. I'm going to reflect these portions of the graph. So the first one I'm going to reflect is the red, the x squared plus 2. Okay. And I'm reflecting it equidistant. Again, it's a sketch, but I like to be pretty accurate. Equidistant from the axis of rotation because that's how it's spinning. So there's my red. And here's my blue. Okay. That's a pretty off, actually. There we go. It's a little bit better. Okay. Anyways, you guys get the picture. So now if this is rotating, I'm going blue to blue and red to red. And that's happening everywhere. Right. So the left picture would be the one that I would draw. The middle picture there showing a single slice, a single washer. And the third picture they're showing the full three-dimensional shape. Okay, so I don't have enough room to work here. I'm just going to move on to the next slide. Same exact problem explained. And I'm just going to draw my slice. So my outer was blue, my inner was red. Okay. So I need a little r running vertically, so it is a y equals. And I need a big R running vertically, so it's a y equals. Okay, so blue was G. And red was F. Okay. And the axis of rotation was negative 3. Right? It got larger. We added 3. So x squared plus 2, the way I had you think about it, though, was top minus bottom. So, which, of course, ends up being plus 3 because it got larger. Same idea with big R. So it's 4 minus x squared, top minus bottom, or 4 minus x squared plus 3, or 7 minus x squared. Okay, so now we've got this idea of pi, big R squared, 7 minus x squared, squared, minus little r squared, x squared plus 5 squared, dx. And that will give us first the area of the shaded region, and when we integrate it from point of intersection, right, far left x value to far right x value, negative 1 until 1. And when we integrate it, it will give us the volume of that solid, which looks like a wedding band, which is why they call it that. With these, I would always double check. Make sure you're putting your radius in correctly. Make sure you're individually squaring each radius, and you have your pi. And of course, your limits of integration. So let me go back. 7 minus x squared plus 5. Good. Both of them are squared individually. I'm subtracting negative 1 to 1 with a pi out in front. So 100.53. So those are the 3 examples that I wanted to go through today. Just recapping real quick. We started with an example that was a solid, right, rotating at about that x-axis, but it was a disk problem. We weren't subtracting a little radius. We had the whole thing. Then we went to a problem that was a washer. Okay. We had to subtract big R squared minus little r squared. But the axis of rotation was still the x-axis. And then our final problem was where the axis of rotation shifted and it made our radius, it stretched it out. It made our radii larger by 3 units. Okay, so we showed that by adjusting our radius and technically adding 3 to both of the functions. All right, have a great day. So today's Monday, May 11th. You will have a second video on Wednesday, May 13th, and then it's a reading day on Friday. So we will actually close out 6.3 by the following Friday, whatever that date is, the 22nd, I guess. And that'll conclude our learning for the year. We'll finish the year with a project, and that's it, guys. All right, so wish I could see you, wish I could actually talk with you. Your emails have been great. I wish you the best, and I'll